and LBNL. So I see the title has sort of expanded. Let's say fundamental QCD in nuclear, and thank you very much.
My pleasure. Thank you. I'm happy to be here at the workshop, and have already had very awesome discussions, specifically about gluon singlets and glue balls. There's actually only going to be one slide on that, so I don't know why I put it in the title. I was just excited after I talked with Anna and okay, so fundamental QCD in nuclei. This slide, I'm not going to show it anymore, but I'm showing it now just because I really liked this article that June Gibbs wrote last summer on the EIC, basically as a QCD machine to study nuclei and fundamental particles. So he says the electron beams at the EIC and the knowledge the collisions of electrons with ions will reveal about the arrangement and interactions of quarks and gluons will help us understand the force that holds these fundamental building blocks and nearly all visible matter together. I like very much framing the EIC as a machine for one of the four known forces of nature. I find that very powerful. Okay, so QCD in nuclear physics and particle physics. Particle physics, I consider fundamental QCD. These are quarks, gluons, and color-charged objects. Nuclear is effective QCD, the nucleons and nuclei, and hadronic physics is subnuclear. And so there is a, should I keep talking?
Yeah, just keep going. Yeah, they're saying the audio is not great. So
Oh, no.
I'm trying to figure out why.
Maybe I should talk really close to this thing.
It usually is pretty good, so I don't know what changed.
Maybe just a little
It's
louder.
selected properly. It's
Yeah,
coming from
maybe
that
okay.
microphone. Which we had that one problem once, but
Okay, I'm gonna try to
everything
talk
looks
louder.
good, so I don't know. I can turn up the gain. Maybe someone touched the
I
dial.
think it's only maximum.
Oh, the gain is way too high, probably. So how about the people at Zoom? Is it different now? Is it better?
No,
I can't hear anymore. I mean,
No.
Here's no. We're gonna have to echo, 'cause I'm on mute.
It's worse. Okay, let's just try to. Okay, how about now? Can you hear anything?
Is it better,
No?
Stan?
yeah, that's better
it's
now.
good on Zoom. It's good on Zoom.
Okay,
It's
great.
good on Zoom. Okay, awesome.
Sorry for the interruption.
No, don't worry. Okay, so so we have these two levels of QCD, the fundamental QCD level, which is the color charged objects, and then the effective QCD level, which is our nucleons and nuclei. Hadronic physics, I sort of just consider that subnuclear, baryons, mesons, a bit of overlap there with both. I mean, actually with nuclear. And so, but the point here is that we have this assumption of separation of scales, which Elena was talking about, which is very important. The assumption that you can do all the kinds of physics you want with your observables and experiments without worrying about, like if we're in nuclear physics, without worrying about the underlying degrees of freedom, the higher energy, shorter distance scale physics. But what's extremely interesting is the boundary in between these scales. And when that boundary is breached, and this is what Ellie was talking about yesterday, which is basically you can have experiments which point you to a nuclear physics effect that's going down into fundamental QCD and vice versa. The fundamental QCD particles showing up in nuclear physics. That boundary and that behavior is very interesting. You can map it. If we pin this down, I feel like you can map this to other fields of physics. Because my background, my PhD was in particle theory, beyond the standard model particle theory. People were very interested. So the standard model is this beautiful, precise, powerful theory, which has some UV completion, some high energy completion that we don't know. It's not complete as it is, but it's very powerful and it works. But if there's any way to access the higher level theory from what we have here at the LHC and all of our colliders, that would be awesome. So I feel like there's a mapping and an analogy that could be made. Okay, so the talk is not going to be as long as it would have been because of Ali's talk yesterday, which is good. Because what I'm going to talk about is basically Diquarks all over the place. Diquarks and their effect on the EMC effect, Diquarks and their effect on these hidden color states in nuclear wave functions, and then some gluon hidden glue states also. Okay, but first I'm going to start with the EMC effect. This is a bridge from QCD to nuclear physics, as we know from yesterday. So these are the deep inelastic scattering diagram with your lepton coming in, exchanging a virtual photon with a single quark, losing energy and exiting. And here is the Bjorkane X variable that he showed us yesterday, which is which just gives us sort of miraculously the fraction of momentum that the struck quark was carrying. There's a derivation in one of Peskin's textbooks, which is just, it's very straightforward and amazing. If you try to, I tried to follow Bjorkane's derivation of his own variable, and it was very difficult. Couldn't. Anyway, so this is the momentum fraction that the struck quark carries. Here's our differential cross section for deep inelastic scattering to happen. Here is the structure function that you pull out of the cross section here, this term. And the structure function is what contains these quark momentum distribution functions. So you have this nuclear cross section, this deep inelastic cross section, which tells you about the quark behavior inside of the nucleon. Okay, so the EMC effect is the distortion of nuclear structure functions from what we expect. Both of these plots are from the 1983 EMC effect discovery paper by the European muon collaboration. And so what they had was the theory predictions in their paper. This is the ratio of structure functions as we talked about yesterday in the discussion. For the nucleus divided through by the single structure functions for your protons and neutrons, and like everything sort of hovering around 1, and then going up here, the Fermi smearing, and then they go and measure it, and it's just the data flatly contradicts the theoretical predictions. And so the question is how, so the question is, look, you have these quarks which are bound into their nucleons at energy scales of like 200 MeV. And the nucleons bound to the nucleus at like 5 MeV. So why should a quark in a nucleon know that the nucleon is embedded in a nucleus? It's a mystery that has not been solved to this day. And so the possible explanations are the mean field effects that Ali told us about, and these local effects, these two nucleon correlations, very short range correlations, or maybe a blend of these. I think somebody just came up with a blend, or maybe that was old. Anyway, so, and there was no reason to favor one versus the other from 1983 up until about 2009, when beryllium-9 didn't fit a simple mean field model. And from this review paper, it seemed like the field sort of shifted in the direction of looking at the already known short-range correlated nucleon pairs in nuclei. That's from Malachi et al. 2014 paper. And the connection in between short range and in correlations and the EMC effects was actually first looked at by Chofi and Yuti in 1990 and 1991. I think yesterday I said it was 1983, but that was just wrong. These years. And later it was found by the class collaboration, by LA collaborators, that these neutron-proton pairs are dominating the short-range correlated pairs. I'm actually trying to think if it was later or it was like, when did people start actually figuring out that short-range correlated pairs were strongly dominated by neutron-proton, this 20-to-1 factor? I think it was after this, but I'm not sure. Anyway, so since that time, we've had dozens of experiments confirming the EMC effect at all different places with all different nuclei. And in fact, JLab right now is running experiments on other target nuclei. Okay, and so what I'm going to present to you is this new model of Diquark formation that's proposed to actually create the short-range correlated pairs in nuclei. So this is going to be a fundamental QCD description of proposed cause of SRC. So the cartoon is you have a proton and a neutron in a nucleus. Here, you have some quantum fluctuation into an overlapping state where a valence quark from one nucleon and a valence quark from another nucleon come closer together than they are to their home valence quarks. They can exchange gluons, which is sort of gluon exchange across two nucleons. And more than that, more importantly, they can also transform into a diquark, which is a fundamentally different object. Red cross blue is anti-green. I'll explain that in a moment.
Can I
Yes,
understand
please.
this QCD-based transition from like that?
Say it again.
Can I understand it as a QCD-based transition, just the degree of freedom change?
Oh, I have never thought about that as a phase transition. I like that idea. No, I've zoomed in on valence quarks transforming into a diquark. And that's it. I feel like your question is what I've been working on, which is, okay, but I'll tell you this at the end. Basically, diquark formation is proposed as the cause of short-range correlated pairs. There's a downstream project, which is, are the short-range correlated pairs temporary, as Ellie said yesterday? Are they fluctuate, or do they stick together for a moment and then dissipate, stick together and dissipate, so that on average 20% are in short-range correlated pairs, but it's not the same 20% all the time, which I think is correct. Or are they the same ones? If they're the same ones, you have to form this overall color singlet. I don't know if I would still call it a phase transition. I have to think about it. Okay, so first, what is a diquark? So as soon as you have your theory of the strong force described by this special unitary group, SU3 color, and so you have the interaction and you have your degrees of freedom, you have your quarks, antiquarks, and gluons charged under SU3, then you know you have these combinations that SU3 that your math predicts are made. So for example, so here's a quark in the fundamental representation of SU3 color. There's many ways to call this thing. You call it a triplet or a 3 of SU3 color. This is the up quark wave function, up red, up green, up blue. The diquark is formed when you have two quarks in the fundamental representation that transform into an anti-fundamental representation. What that means is that the diquark has anti-color charge and is a different representation of SU3 color. It's really a different object. It's not just two quarks exchanging gluons. So here is a wave function for a very specific diquark, an up-down diquark, which is spin 0. The square brackets mean spin 0. And you see it's an anti-symmetric combination of your ups and down quarks here. Okay, so like quarks and gluons, diquarks carry color charge, so you can't see them directly. So there's no direct evidence for diquarks, but this has been a long-term work in progress together with Stan and a couple of others on diquark detection experimental proposals, both for JLab and also for the EIC. There's a change in the jets from collisions when you have a diquark ejected versus a quark ejected. Diquarks pick up one single quark, so you're going to favor baryons in your detector, as opposed to, you'll never find a meson if you have a diquark jet. Okay, and there's very strong evidence that that diquarks, indirect evidence that diquarks exist from baryon mass splittings, which I'll show you in a minute, and the Reggie slopes, so the mass squared versus orbital angular momentum for mesons and baryons, they have exactly the same slope, which is an indication that their internal structure is the same. So diquark is a baryon two-body structure, and quark antiquark is a meson two-body structure. Okay, so what are diquark-induced short-range correlations?
So before this, what fraction of the photon wave function is di plus 1
Is what?
versus 3?
What fraction is what?
What fraction of the photon wave function is diquark plus 1 other than 3 individuals?
Well, that is the question. So that's what I'm trying to get at. I'm going to answer that question as best I can during this talk. And before I started talking, when you were looking at color superconductivity, I had a slide up here and I was asking you about the proton wave function, but I'm going to ask you at the end.
But roughly speaking, talking about the big piece of the wave function.
No, I have no idea. Okay, look, the indirect evidence, which I'm going to show you, indirect evidence with some assumptions looks like 50-50, a proton in a 3 valence quark configuration versus
2 plus 1.
2 plus 1. 2 of these quarks have fallen into the attracted diquark potential and they're sitting like this exactly.
Okay, so it says it's big, essentially.
Yeah,
Presume.
yeah. 50-50. And then if you go to holographic light front QCD, right, this whole subfield of QCD with great calculational power, they have 100% in quark diquark configuration. No 3 valence quark configuration.
What does it mean that different ways of programming it give you different amplitudes?
How could we have no talk?
By the window, by the
There
window.
is,
Yeah, I'm so happy. Okay, so basically, the proton wave function would be and sorry, I'm not putting the flavors in here.
Yeah, plus a bunch of other stuff.
Thank you very much. Exactly. And what was your question again?
My question was, you said there's different calculations of the diquark components of the beta, I guess. What does it mean that different calculations give different? Is it fundamentally somehow model dependent, or is it just different assumptions, approximations being
It is-
made by different?
It is different assumptions. In my work, I'm assuming I have no idea what alpha and beta are. So I have to do everything as if I don't know which one it is. For this whole subfield of QCD, holographic light front QCD, the assumption baked in is that alpha is 0, beta is 1. And that's how they get these powerful hadronic mass spectrum and spectra and all this stuff. But yes, assumptions from the beginning.
Excuse me,
Yes,
just a
tell me.
simple question. I understand the terminology. So when you see valence quark,
I mean, none of the C quarks. So I mean, there's a proton.
Can I ask one question?
Wait, I'm almost done answering Elena. Here's your valence quarks. And then here's the C, right? The blue one C, which is splitting into quark and diquark pairs. And then maybe returning, it's not going outside its boundaries, maybe returning to each other. So I'm distinguishing the valence quarks, right? Which set the quantum numbers, kind of, they don't really actually, set the identity of the proton in a way from all the C quarks.
okay.
C
I see.
quarks are quark and diquark pairs,
Okay.
right? So they sort of cancel each other out as far as quantum numbers is concerned.
So it's like a long time scale.
Yes,
quark,
I
right?
understand, because I was wondering, because you were distinguishing valence quarks from quark plus UD. So that's why I'm wondering.
Yes, good. Okay, and so valence quarks is this guy. So 3 valence meaning and no interactions in between these 3 valence.
Uncorrelated.
Uncorrelated,
Okay,
exactly, very
okay,
good.
okay.
And
So
then,
that's all.
and then here is the other one. Because as I'm going to show you, there's a strongly attractive potential for these 2 guys to create a diquark. So these guys are going to be a diquark, and then you have all the C stuff here. DU bar or DD bar, SS bar, whatever.
But they still interact.
Say it again.
They still interact. So
Yes.
of course.
But all the C, because the EMC effect is in this quark momentum fraction range from like 30% to 80%, 0.3 to 0.8. This is the valence quark region. That's what we're proving, is the valence guys and not the C guys.
Okay.
So all of this is assuming that I'm really only dealing with the valence, what these are doing. Sorry, somebody had a question on Zoom?
Shujan?
Yeah, I have one question. So I'm a little bit confused. So for this quarks, valence quarks are bounded in the proton neutrons, how they can form a diquark. I mean,
How can they form a
difference-
diquark? By the group 3 rules of taking a 3x3 into a 3 bar, or which equivalently comes along with a short range interaction, a short range potential, which I'm going to show you.
okay, so you don't need a deconfinement. You just can.
Oh, absolutely not. No, no, no.
Okay.
No, I mean, I don't need deconfinement yet. There is some funny business with deconfinement in the future, but right now, no.
Are you going to talk about the size of the diquark system?
No.
How big is it? How big is it? I mean, like how strongly they're.
Okay, so this is something that, okay, so this is something that people who really know QCD have disagreed upon. So in my opinion, and again, there's at least one senior person who doesn't agree with this, but in my opinion, the Reggie slope, the fact that the Reggie slopes for baryons and mesons are equal, tells me that the baryons are in a quark-diquark configuration, and not only that, but that the quark-diquark configuration is something like a 2-body one, which means that the diquark is smaller. It's closer together than just 3 valence quarks would be. But I think somebody else could make the argument that all you really need is those diquarks to be correlated, as opposed to also being very close together. In my
Be close in momentum space. But
Yeah.
not
So they don't necessarily have to be well localized spatially, you're saying.
Well, I think they do personally. In order to feel this interaction and to stick together. What happens afterwards, maybe they can extend. I don't know. I don't think they do.
But if the diquark is very small, by definition, they must have a large and opposite momentum, right?
Is that a problem?
No, I'm not a problem. I think they probably require, I mean, in order to have a large momentum correlation, they probably should be small.
Yeah, I think that you're right. Yes, I think that you're right. And there is this proposal. So I was just at this meeting for the energy upgrade, a proposed energy upgrade for JLab. And one of the pieces of physics that was discussed there are these super fast quark studies, which is what you're saying. It wasn't diquarks, but like hidden color in the deuteron. So yes, things that are very close together that have very large relative momentum. So the answer is yes. Yeah.
So this might be the same, a different way of asking the question I asked yesterday. And
Okay.
if so, you can just let me know.
Okay.
But so if you look at some of the phenomenological predictions for D over U as you go to X of 1.
Yes.
Like the ones by like Close, Farrar and Jackson, etc. Basically, these different predictions have to do with different methods for which 2 quarks are kind of forming a diquark spectator.
Yeah.
To me, the implication of that then is that if you have quarks that are part of this diquark pair, they're less likely to be at high momentum. So you know, if 2 of your quarks are in a diquark spectator, then it's the third remaining quark that is the most likely to be found at very, very high X. So is there some reason why quarks in a diquark pair are moving slower or are less likely to be at high momentum?
Okay, so the diquark, okay, so if you're out here looking at the physics of XB equals 1, you're looking at a quark which contains, the momentum fraction is 1. It contains 100% of the momentum of the nucleon it belongs to. In that configuration, you've got 3 valence quarks, right? If one of these guys has all of the momentum of the nucleon, I'm gonna go over here. If one of them has all the momentum of the nucleon, it cannot be one of these guys in the diquark. These guys are
Because
sharing
those
momentum.
those have to be kind of together.
Yes, exactly. So if we're talking 1 nucleon, these guys are going to be, max is going to be 0.5, 0.5, and 0. That's the case. So So that's the reason, yeah, the scalar Diquark, I forgot the D over U plot, but I know the scalar Diquark like goes out to,
Right,
oh, D over U goes to 0.
right. For the
Yeah,
scalar Diquark.
and
And then for like,
it goes to 0.25 for the F2 ratio. That doesn't matter.
so and in those papers, when they talk about, when they use the term Diquark, are they, is that the same as what you're talking about? Or is there some kind of nuance to when you use the term Diquark here? Is that different?
Like, okay, so I'm going to show you at the very end of the talk, is in the backup slide, the proton wave function according to nuclear physics papers. So I'm working in collaboration with Simonetta at UT right now to try to translate the normal proton wave function into my language, into the sort of, into this language here. And what people are calling in that 5-term proton wave function, they're saying this is the scalar Diquark, right? It's the capital S00, and then the T01 or whatever. They're calling those Diquarks. I don't know that they are Diquarks in my definition. I think they are objects. I think they are objects that are exchanging gluons. They're 2 quarks. They're exchanging gluons. They're spin correlated for sure, because the coefficients of that wave function are all the spin, the Klapsch-Gordon coefficients. But I don't see a Diquark bond there. I don't see the mass lowering for the scalar and then the mass increasing.
But, excuse me, they are Diquarks. They are the Diquarks in the model, in the spectator model.
Yes.
I mean, are Diquarks. I mean, I don't know what you mean. That
When I'm saying that I don't know that they're Diquarks, what I'm saying is the coefficients of those terms look to me like they are spin coefficients. So you have the spin singlet, and then the spin triplets, isospin singlet, isospin triplets. I don't see a group theory factor in there. That's my point.
No, okay. There is the flavor also, right? So that translates directly into flavor. So that's where the group is the flavor.
No,
it's SU2.
Right. So when I say isospin, when I say isospin, I mean flavor. So, but yes, you're totally right.
Yes.
There's a flavor component to it also. That has nothing to do with the group theory factors I'm talking about.
Okay. Their color factors are not so there is a standard configuration for their color factors. So they just give a color singlet in the end, the combination of these particles. But I agree with you. That's probably what you mean. That there could be many more color configurations, or not.
No, I mean something different. And I just thought about this either yesterday or the day before. So we're going to have to talk about it, and I do have a backup slide about it because I'm not 100% sure, but I don't see. I seriously, I don't see the group theory transformation. I don't see the QCD transformation there. I do see diquarks. I see 2 quarks stuck together with spin and isospin. I do not see them stuck together with color.
Yes, but the isospin, the spin and isospin translate into yes, exactly. The U and D quark components. So these are U or UD, constituents. So
yes, but like that's sort of that you can think of that as like maybe a molecular description of it versus what I want to do is say.
Oh yes, absolutely. Yes, I agree.
What I want to say is it's no longer an up and a down. This thing is up crossed into a down, which makes an up red crossed into a down green, which just makes
Jennifer, I agree. Yes, you made it clear. I think. Yes,
anyway,
okay. They're molecular configurations. Yes, they're not diquarks per se. Yes.
Well, we have to figure out what that means, but we'll do so. Okay. Everyone? Okay. So thank you everyone for your questions. Okay, so what are Diquark-induced short-range correlations? Ali already went over this, about the 20% of nucleons that are in these short-range correlated pairs, how they're always or almost always above the Fermi momentum of the nucleus, which is around 250 MeV per C. So Diquark-induced short-range correlations, what is the model? The model, so first of all, what causes the short-range part in this model? It's the same quantum fluctuations into an overlapped state. Quantum fluctuations in the separation distance or quantum fluctuations in the relative momentum between the two. How short is the range? Well, you can take the Fermi momentum, 250 MeV per C. You can translate it just using natural unit conversion to a center-to-center separation distance of about 0.8 Fermi. And I think you were saying that you separate them by about a radius, roughly. So closer than the center to center of the nucleons is closer than about 0.8 Fermi. It's sort of roughly. If you remember that the radius of the proton is about 0.84 Fermi, these things are very close together. And I'll show you a plot of the overlap.
Is that relevant radius for you? Because that's the charge radius.
Yes, I mean, it's fine, I think.
Yeah, I think it doesn't change. This is ballpark numbers anyways, right?
These are ballpark numbers. No, does it go down that small, the mass radius?
The mass radius usually larger than, I mean, I don't know for nucleus, but for nuclei, I think the mass radius is usually larger than the
From 1% and it's smaller. It is smaller. It should be smaller by actually quite a bit.
Yeah.
So maybe you.
No, but I think, no, but the charge radius is actually what I mean, I care about both, to be honest with you. But the charge radius is really what I care about, because what I care about is how close these charged particles are coming to each other. The ups and downs, the valence quarks. So this is extremely relevant. It is the only relevant one, actually. Okay, so there's very large overlap, wave function overlap between these nucleons. And then what causes the correlation is that a diquark is proposed to form across the nucleons. So these valence quarks fall into a QCD potential and fall into a QCD potential, and this highly energetically favorable up-down spin zero, isospin zero diquark is created. I'll show you how. Okay, so why is it just the spin zero, isospin zero, up-down diquark that's created? So these are the options. These are the guys that can form across a nucleon pair or anywhere. You can have your spin one, isospin one, the triplet, isospin triplets here, up, up, down, down, up, down. The parentheses means spin one, that means vector, and then the brackets means spin zero. This is from Bob Jaffe's 2003 paper. He calls this one the good diquark, and these guys are the bad diquarks. And the reason is because when you go out and you measure baryon masses that contain diquarks, and you figure out the diquark masses, you find that the scalar diquark is 200 MeV lower in mass than the vector diquarks.
Sorry.
Tell me.
So this is, maybe I missed it before, you're assuming this only happens in a relevant way between valence quarks. You're not considering diquarks in this, like, with the C quark.
Yes, because the reason why is because, again, we're in the EMC effect region. So what I'm trying to explain here is the EMC effect. So I want to know what's happening with the valence quarks. With the overlaps that I'm showing here, yeah, you should have C quark interactions also. But the C quarks are different, right? Because the C quarks, you have a gluon coming off some other valence quark or whatever. The gluon is an octet of sp3 color. It splits into a QQ bar pair. That's an octet. This is not it's not a meson. It's not a color singlet. So in order to capture one of these guys from a neighboring nucleon that's overlapped, I think it's more complicated. I think it's doable, but I think it's more complicated.
Yes, I mean, this would
So
be your dot, dot,
the
dot,
things
right?
have to reconfigure themselves. Does
This
it
would
make
be in your
sense?
dot, dot, dot.
Yes,
right?
tell me.
Yeah, so like there's like all kinds of gluons plus C quarks.
Yes,
and that would be
absolutely.
one of them. And what you're making is an argument why that particular thing should have a small amplitude.
Oh yeah, I should have a really small amplitude, because what you're talking about, you're saying, okay, I have a proton with 3 valence quarks. This is a color singlet. One of these guys emits a gluon. This is a color octet. The octet splits into a QQ bar pair. This is again an octet. If you want to take off an octet here, that's fine. And then combine it with a fundamental, a 3. 3 cross 8 is, I don't know off the top of my head what 3 cross 8 is, but you form some new object, right? That new object has to form some kind of color singlet here, and you've left over this guy, which is hanging out. I'm guessing it translates back into a 3 bar.
Yeah, I guess my question is this a dynamical effect that it's smaller? Is it a pure group theory effect that it's
What do you
smaller?
mean by dynamical effect?
like also supposedly these are processes at some momentum scale.
Yeah.
And then you have to look at the running coupling of QCD and say maybe it's, sort of diagrammatic way of generating this component.
Yes, dependence is different. So she's in a region where it's dominated with largest. So you would have much less of the C quarks sitting also in this.
Yeah.
C quarks are dominating a very low X. So you would have to combine very low X with very large X. I don't know if that is possible.
Oh, that's another factor in it. I'm just worried about how you recombine everything into a proton.
Yeah, I mean,
region.
I think.
But this is the best explanation, which is that right now we're in the valence quark region of pure KX. The C quark region is going to, things are going to happen. Even within a proton, Stan and I have a diquark capture theory, which is, or model, whatever, which is that when you form a UU bar pair, you can have the D quark capture this U and form a diquark here. So the 5-quark Fock state of the proton is going to have some pieces of this, of C quark interactions, exactly what you're talking about. But for where I am right now, the C quarks are going to be negligible.
So it's a kinematic selection basically you're making, and that translates to a suppression of.
You said it better than I could, yeah. Okay, so here are the options of diquarks that can form anywhere, across a nucleon or anywhere. And then I just told you that this one is the lower in mass by 200 MeV, so that's the one that sort of lowers the mass of your system or is energetically favorable. You will notice I don't have any different spin isospin values here, like the spin 0 isospin 1 UD prime diquark. But it doesn't work because anytime you build a diquark or a duo diquark or any of these color charged objects, you have to build the wave function for them. And the wave function, each component of the wave function has to be included. And you know when you're building a diquark out of 2 quarks, fermions, that you need to pick up a minus sign and exchange your quarks, your fermions. So here's the components for a diquark wave function. You have the color component, this is QCD, group theory. It's anti-symmetric by design, because that's the one that's strongly attractive and forms a diquark. An imposed assumption here is that I want the absolute lowest mass object to form, because I'm saying there's a quantum fluctuation of nucleons, and there has to be an energetic reason for them to stick together, even momentarily. So I don't want an L equals 1. I don't want a high mass state. I want a low mass state. So I'm imposing a symmetric spatial component, and all that means is that spin and isospin have to be the same. They both can be positive, they both can be negative, but they can't be different. And spin statistics constraints come in strongly when I'm talking about glue balls and especially the 2 gluon glue ball candidate for the problem. Okay, what are the requirements for a diquark to form in the nuclear environment? We need strong overlap so that the QCD attractive short-range QCD potentials can act. Also, the potentials have to be attractive. So there's all different kinds of QCD potentials that you can calculate in SU3. You can find strongly attractive ones, weakly attractive ones, strongly repulsive or weakly repulsive. For this model to work, it has to be strongly attractive. And then you have to have some significant binding energy for this object to form, to lower the mass of the system. So it sticks. Okay, so here is the overlap. So again, this is just natural unit conversion between measured relative momentum and the spatial separation in between the nucleons. So this is from class data on carbon-12. And what they were looking for is when the crossover between neutron-proton short-range correlated pairs changed to picking up some proton-proton short-range correlated pairs. So, and they found that when you have relative momentum of 400 MeV per C, you have your, in this 20-to-1 NP dominance. And then when you go up to 800 MeV per C, you start seeing some neutron-neutron or proton-proton short-range correlated pairs. So I'm just plotting the separation distance that corresponds to 400 MeV per C. It's about half a Fermi. This is how much overlap we have. If you calculate the intersection region, it's almost 60% of the volume of each nucleon is in the overlap region. Here, when you start looking at proton-proton, or you start finding proton-proton short-range correlations, you have a natural unit conversion giving you a quarter of a Fermi center to center separation distance between your nucleons, which is almost 80% of the volume, of the nucleon volume in the overlap region. And the point of this is just to say it would be really weird if QCD interactions did not occur between objects from different nucleons with this kind of overlap. Okay, so that was number one. Do we have strong overlap? It looks like yes. Number two, the quark-quark potentials in QCD. So here's the short-range potential formula. So it's a 1/r. This is the gluon propagator times the vertices. So these are the group theory factors that you pick up. These are the representation matrices. You're exchanging a gluon between a given representation R and another representation R prime. So you can exchange a gluon between a quark and a gluon, or gluon and a gluon, antiquark, antiquark, whatever. For us, for the diquark, R equals R prime. When you actually calculate this thing out, you need to know not only the two representations that are exchanging a gluon, but what your final representation is. And so you end up, this is a textbook problem, but it's kind of hectic in my opinion. But what you end up with is these quadratic Casimir operators, which give you, which you calculate for the final state representation, anti-fundamental for diquark, and the initial state representations. And what you get is you get the coefficient in front of your QCD Coulombic potential. It can be positive or negative. Negative means attractive, positive is repulsive. And this factor tells you the strength, 2/3 of the strength. So the diquark is bound and the strength is big. What do I mean by big? If you want to form a color singlet, for example, a meson, you can calculate the same QCD potential and it is twice as strong as the diquark state. So so the diquark is bound and it's strongly bound in terms of QCD interaction strengths.
So, sorry, question here. At some point along the way, you're making a non-relativistic reduction of this. Like, I guess I wonder, like, you're writing down the Dirac propagator there. So why do you not need like a Peter-Salpeter like equation?
To do what?
To treat a bound state. Because normally when you start, it looks like you're starting from something relativistic, and the potential you're writing down looks like a non-relativistic potential between these objects. There must be some sort of non-relativistic reduction along the way.
If there is, okay, so what I'm doing, I taught this to myself out of Peskin's textbook, his 2019 textbook. And he usually tells me if there's assumptions happening along the way, but he does this calculation with this formula, and the conclusion is the diquark is bound, quote unquote. So I think that's a valid and very interesting question, which actually I have also, and I'm going to ask him about it. Because maybe there is an assumption I just don't know about. Yes.
There is also an assumption that the gluons basically aren't confined in that potential. It's the same potential that you have for electrodynamics, for electrostatics at least, except for the color factor. At very large distances, that shouldn't be true. There should be something that goes as R, but
large distances, you mean like confinement scales? Like
yeah.
Okay, that's fine.
I mean, obviously, this is something with a limited domain of applicability, but for the case of this exercise, I think it's valid enough.
Oh, it is valid because I'm talking. Did you see the distance scales I'm talking about?
Yeah.
We're talking less than the confinement scale, so less than a Fermi.
Yeah.
We're good. We're good to go.
Yeah, you have no requirement for the quark flavor, right?
No, at this stage, no. There's no requirement. So yeah, this happens between DD, UU. Okay. Okay, so the quark potential is strong and it is attractive. And then we want to calculate the diquark binding energy. We know how to calculate binding energies. you find the bound state object, measure its mass, and subtract that from the constituents. But of course, since we don't measure the diquark mass, we have to go and find baryons that contain diquarks, which are the lambda and the sigma diquarks. Here's their diquark-quark content. And what people do is they use either the baryon or the meson mass formula. These were originally from the Rugila, Georgi, and Glashow paper in '75. But I used the Karliner and Rosner 2014 paper and the Gaziorowicz and Rosner 1981 paper because they explain the baryon mass formula very well. So basically, you have the measured baryon masses here, and then the formula just says the baryon mass is the sum of the constituent masses. Constituent masses, I mean effective masses. These are not like 3 MeV. These are like 350 MeV. So they have all their quarks, quark, antiquarks, and gluons around them. So you sum up the 3 effective masses of the quarks in the baryon, and then you know you're affected by a QCD hyperfine interaction, so spin-spin interaction of color spinning objects. In order to find what I'm looking for the diquark binding energy is I'm looking for the mass of the lambda, which has the scalar diquark in it, which we have here. And the quark content, I need the effective masses of up, down, and strange. So basically, I need 4 baryons that contain the quarks of interest, and I need to just calculate the spin-spin interaction in order to solve for the 4 unknowns. 4 unknowns meaning the weight of the hyperfine interaction and the effective quark masses. So if you do that, solve your 4 equations, then you find that the mass of the up and the down, which are assumed to be equal, are 363 MeV. Strange is 538 MeV, I think it's plus and minus like 5 MeV, and your binding energy for the scalar diquark to form, not the vector diquarks, is about 150 MeV.
Yeah. So how about the omega 3s quarks? This will be interesting.
Yeah, actually, it would be interesting. And no, I'm not dealing with that thing for the same reason, because I'm not in the C quark regime. But yeah, it is an interesting question. I'm only dealing with valence quarks here. Like, people love quark nuggets, and strange quarks, 3 strange quarks or more strange quarks are considered to be quark nuggets.
No, so omega. So that's what you asked.
Yeah, yeah.
So
I thought he said 3 strange quarks.
yeah.
What the-
So that's just 3 omega is 3 strange quarks.
So I don't know, like Whitten was doing quark nuggets, I think, in the 80s, and maybe he was putting a bunch of omegas together. I don't know. It's something I'm interested in right now. There's a paper that came out last week. But no, I haven't touched strange or anti-strange. Okay, so we have the overlap. We have the attractive short-range QCD potential that forms a diquark and a significant binding energy of the order of QCD binding energy. Okay, so the model is plausible, is my argument. And then what are the implications of this thing if it's really a diquark across nucleons that's sticking nucleons together? So the implications are going to come from the quark flavor dependence of the low mass diquark that forms across nucleons. Okay, so specifically what I was looking for were the NP versus NN and PP short range correlations in A+3 nuclei. So basically this is just a counting argument saying, okay, what are the quark ingredients of tritium and helium? How many different ways, like how many different microstates are there to form UD diquark across nucleons with these quark contents, 5 up, 4 down, 4 up, 5 down. This is complicated by the fact that I have to consider 2 different scenarios, which is written in blue at the top, which is that our nucleon is considered to be in a linear superposition to first order of a 3 valence quark structure, no diquarks formed, and a quark diquark structure. So I have to consider both of these cases separately. So in the 3 valence quark, the number of ways that you can form a neutron-proton short-range correlated pair are 60% and 40% same nucleon. And it's exactly the same for the helion, 60% and 40. If you go into the quark-diquark configuration of your nucleon, then you see, this is for the tritium, the only way you can form a scalar up-down diquark across nucleons in tritium is with a proton and neutron. And exactly the same, but flipped for the helion. So basically in this configuration, what you predict for the types of short-range correlated pairs in A = 3 is 100% neutron proton. So what this gives me, sadly, is not a number, but it gives me an inequality. So I know that in helion, the ratio of PP to NP SRC has to be somewhere between 0 and 0.4. If we find it to be 0, this is under some assumptions, it's not something definite. If we find it to be 0, it would indicate that alpha, that this coefficient is much bigger than beta. And if it's more towards 0.4, you would think that beta is bigger than alpha. And so what happened, I actually honestly didn't know this at the time when I was writing, but JLab had actually done an experiment. It was a part of the marathon experiment that actually was measuring this ratio. They were interested in the ratio of PP to NP in A = 3 nuclei. And what they got was a value of 0.24. So it's something like, it's almost in the middle, but more towards the 0.4 end of this. So like alpha and beta in this simple picture, alpha and beta are about equal, maybe a little bit more alpha in this. Okay, and so the two caveats are, in these overlaps are so strong that you could imagine, even if you had a diquark already sitting in your nucleon, you could break it up. Like you could have another quark from the neighboring nucleon be so close that it could actually take one of these quarks and form a diquark with it. So that's something that could happen that needs to be looked at by me. And then also, this is the nucleon written to lowest order. As we said, we have a ... here. And I have a question about this. I wrote this because of Adam's question from a while ago. What I wrote is there will be corrections in the form of spin 1 diquarks to this picture. So one of the plus is going to be plus a gamma times a spin 1 diquark instead of this guy. But that guy is 200 MeV more massive, so it's really going to contribute a lot less. But it's still something that needs to be looked at.
Sorry.
Yes.
How do you count that mass? Because it's confined, right?
Okay, so the mass, right? So the masses of these guys are calculated from using baryons that are shown to contain these diquarks. Their isospin values and their spin values, they're shown to contain these diquarks.
So you're assigning, it's sort of like quark masses, which are also, not perfectly well defined because they don't exist as asymptotic particles in the same.
These are effective quark masses. Effective. So it's basically, so the proton would have 3 of these effective quarks in it, like 300. Well, it turns out to be 363, but you can see it would be about 350 MeV for each one.
So this is all within the quark model picture that you assign an effective mass to the diquark.
Yes. Which is related to your question from before, which I have been very curious about, which is this is a relativistic treatment. This is non-relativistic, right? We have effective quarks here. And if you compare their mass to their momentum, you can see this is acceptably non-relativistic. But the other question about using the short-range QCD potential, that's an open question.
Yeah, I think it's sort of a standard thing to do. I was just wondering what's the argument. There's also people doing this.
There must be.
Sure. Then what are their arguments for doing it that way?
I think it would help me to actually read what they are doing, what the thinking is, and also ask them, see what he meant. In fact, we had a discussion about this last week. Me and Stan Brodsky, Guy Determont, and somebody else, and there were 2 different opinions on whether an assumption was being made or whether it was not being made. Anyway, so I will get back to you. I will get back to me and to you about that.
What happened to this energy? We didn't found that energy. What we do with it?
Okay, what do I do with that energy? Okay, so you have this binding energy, right? The 150 MeV binding energy. What happens to it? Is that your question? Well, I think it lowers the momentum of the system. I think it removes quarks. I think removes the quark distribution function is depleted in certain areas due to this lowering of the mass.
Faster, not slower.
Say it again.
You gain energy, so you have now more energy. It should be faster, not slower.
What should be faster and not slower?
Whatever. If this energy came up to be kinetic energy, then something should move faster, not slower.
I
I
don't
don't know what the percentage must.
Well, I don't know. Ellie, I mean, think of another situation where you lower the mass of the system by binding a nucleus, a helium-4. What happens to the system? I actually don't know the answer to that. So
That's the mass.
say it again.
That's the mass.
Yes, when you lower the mass of the system.
No, you slow down the nucleon. Effective virtuality offshots of the nucleon when it has the helium.
Oh, is that right? Yes.
Well, the highly bound systems are going to be much smaller in spatial size. So just from the uncertainty relation, you know, on average, the kinetic energy of particles that are confined to that volume are going to be larger on average.
Makes
So
sense.
the
That makes
particle
sense.
should be going faster.
Ellie, what do you think of atoms explosion? I like it.
The kinetic energy of the pair.
Yeah, or all 6 quarks, because they're all highly.
All the relative momentum.
Yeah, I'm just wondering if it's combined to the diquark, the newly formed diquark, if it's also dealing with 6 quark object. But yes, effective. I like that. It's gonna. You can get more compact. If it gets more compact, then the kinetic energy increases. I haven't thought about that. The reason I
Sort of,
Yeah.
sorry, but I mean, the only thing well defined is the overall energy of that nucleon, right? And even if that nucleon is bound within something else, then even that is not something that's defined independently of the rest of the system.
Yeah.
So to some extent, I think we're talking about fluctuations here in components in the wave function, right?
yes.
So feels to me like these questions are sort of ill-posed. You said like what happens to it because you cannot see that thing in isolation from all the other amplitudes. And it's just somehow the energies and momenta have to combine so that overall for the nucleus that you're talking
Yes,
about,
yes.
plus whatever obstructs the nucleus, that energy is conserved.
Yes.
But independently, none of these things are actually conserved.
Well,
So
I mean, what you say makes sense, but like for me, I have to think about this thing physically in the sense, and maybe it's just not a good way to think about it. But like for me, I'm like thinking here, I have this quantum fluctuation. What happens when you have a quantum fluctuation into this unlikely state? It dissipates immediately, right? Fluctuate, dissipate. This is what happens. Something has to stick that thing together. You have to lower the energy, then lower the mass of the system even temporarily. Maybe you're saying that's not a precise way to think about this, but that is the way I think about this.
Well, it's like using a time-independent formulation.
Yeah.
And I mean, the intuitive argument is always based on some actual time dependence, you know, it's a situation and it's probably that's fine because it's all strong interaction and very short time scales as opposed to that thing hitting the middle. So it's probably fine. But these things, when you wonder like, okay, is energy conserved there? To me, it feels like we want to describe the EIC effect, right? So you have something scattering off the nucleus. So you have like these layers of things, and the only thing conserved is the overall energy of that process that's happening at the collider. But none of these individual energies or momenta is actually conserved.
But you care about what happens to the individual momentum. I mean, what's happening, what you're measuring effectively is the quark momentum distribution function. You need to know what's happening.
Well,
to
but you're
it.
measuring that under some scheme assumptions again, right? So you're measuring count rates and you want to relate that, extract something, and like quantum distribution functions are always written under some theory assumption. What is the
But forget what the part-time distribution function is. What I'm saying is that Q of X or F of X, however you want to write it, is inside F2, it's inside the structure function. You need to know, yes, it's going to be model dependent. You need to know what that guy is. You need to know what is happening to quarks momentum in a very precise way. The 3 valence quarks with charge 2/3 squared, 1/3 squared. You need to know this very precise information. Regardless of what the PDFs are going to be different depending on the models. But you need to know them precisely, right? Like maybe I'm not understanding what you're saying.
My only point was, we were wondering like, what happens to this energy, like,
It's probably not legitimate version because DT is small enough, you cannot ask questions.
yes.
Or answer questions.
Yeah, so I'm saying, don't worry about where the energy goes, because it goes.
After a short time.
Yeah, it goes somewhere. It feels to me like it's not a concern because it shouldn't. All of the intuition is always based on energy conservation, right?
Yeah.
You're saying you lower the mass,
Yeah.
and it goes to kinetic energy.
Yeah, yeah.
But that is based. The implicit assumption is that energy was somehow conserved.
Yeah, yeah.
And my argument is it's not, because you're looking
time
at
is
the
short
bigger
enough.
picture.
Again,
No,
I get it.
time is short.
If the time is short enough, yeah, but then you have to be very, very careful about the time scale.
Yeah.
Yeah.
It's determined time.
Yeah, and I'm going to say something in a couple of slides that actually is related to this question. But anyway, okay. So this is just an argument that's probably this is just an argument for saying that when you lower the mass of the system, you affect the momentum of the system, regardless of the exact relationship between energy and momentum. Here, I'm giving quarks Fermi momentum in a nucleon. Which I wouldn't have normally done, but Misak Sargsyan, one of his students, did it in a talk. So I felt I was okay to just try and play. And what you get if you assume this Fermi momentum and a certain Fermi energy is you get a depletion of the momentum of the quarks by about 10%. The only thing I want you to take away from this slide is that when you decrease the mass of the system, you affect the momentum of the system. And distorting the momentum behavior of quarks in a nucleus, in nucleons that are bound, is what I'm trying to do. What we're trying to do. Okay, how much time do I have?
We're into the question time already,
No, you
but we had
said-
tons of questions, so that makes sense.
Okay.
But
So,
the whole thing's supposed to wrap up at 12.
So, but then you can continue if you want to.
Yeah, we have the whole afternoon also, which I'm sure we will
oh yeah, we can discuss.
spill
it
over.
after.
So, but we probably should at least try to get to the end of the slides by
Okay,
then, and
I'll do
then,
it fast. Okay.
and then we'll continue the discussion after lunch.
Okay, very good. Okay, so that was Diquark-based short-range correlations. And now I'm going into Diquark-based hidden color states, specifically a 12-quark hidden color state called the hexadiquark. This is proposed to exist in the core of all A greater than 3 nuclei. Okay, so what are hidden color states? These are rigorous predictions of SU3. What they are is they are color singlets. I'm using as an example the helium-4 nucleus. Here's the dominant state for the helium-4 nucleus with a coefficient of NNPP. So the dominant state is a bag of color singlets. Your proton, neutron, proton, neutron. And then you're going to have hidden color states also in here. By hidden color, what I mean is you never form a color singlet until the very final step. So it's a single color singlet. That's what hidden color is. And so this is based on work together with Stan and Guy, Yvonne, and Fred from 2021. Right. So color singlet states, they have the exact same quantum numbers as the nucleus. So they should be in every single nuclear wave function. Typically, when you build these things, because of spin statistic constraints upon quarks and also diquarks, as soon as you have bosons, when you exchange them, you cannot pick up a minus sign, and you often do. So you have to go to like L = 1 or some high mass, spin 1, spin 3 states. So my point there is typically hidden color, the coefficient for hidden color is expected to be very small because these are highly virtual, highly off-shell states. but the hexadiquark is a special object because it is a low mass object. So hidden color has been thought about for 40 plus years. There's hidden color in the deuteron. I'm working on the coefficients for the hidden color states in deuterium right now. They're hidden glue. Okay, so basically the color singlet formed of two gluons, which is what we were talking about for a Pomeron candidate, also has the same quantum numbers as the pi zero. So that would be like a hidden glue state inside of the pion wave function, which I think people call something else, but people have been studying this. But for the glue balls, hidden glue and glue ball wave functions, you have to do the exact same thing. Build the full wave function, make sure you obey spin statistics, and this puts constraints on observables. Tetraquarks and pentaquarks would be hidden color in plain sight, if they are color singlets. So for example, with the tetraquark, if the tetraquark is a CC diquark crossed into a U bar D bar diquark, so it's a compact configuration, a single color singlet, this would be a hidden color in plain sight, and this is what looks like tetraquarks are. And here's the mesonic. It also could be a mesonic object where you have two mesons molecularly in a molecular configuration. And the same for pentaquark, you could have a 5-quark color singlet or a 3-2 molecular state. This is the hidden color, the object in helium-4, again, the hexadiquark. This is the build of the hexadiquark. 2 neutrons, 2 protons. The exact same mechanism occurs across nucleons, which is that you have a new diquark formed across 2 nucleons. When you make the wave function build for the hexadiquark, you have to use weird interactions, weird QCD interactions, the symmetric 6, in order to obey spin statistics and stay at low mass. This is a weakly repulsive bond. The factor is a 6 in front of the 1/r potential. And so what that means is that this guy is not going to be super compact first. And second, that there's the possibility to actually excite the bonds in the duo diquark stage. This is the 2 diquarks crossed into form a 6 bar. So you can excite interactions in between the 2 diquarks there, which can give you very low energy excitations, possibly. And that's work that it's a preprint. We're dealing with the referees right now by Valery Kubarovsky, Stan, and myself. And it's basically just a standard model explanation for this X17 object that's proposed as like a new either dark matter candidate or dark sector mediator candidate. From these these interesting experiments on carbon-12, beryllium-8, and helium-4. Anyway, so I think this is going to be the last. Is it the last? Yeah. So this is the last slide. So basically, the hidden color hexadiquark is proposed to modify quark behavior in helium-4 and higher nuclei. The diquark-based short-range correlations are acting in A=3 and A=2. Hexadiquark does not act in A=3. It cannot, because it has 12 quarks, not 9. So what this says is that you should see different behavior. You should see a break in behavior for the EIC effect and short-range correlated pairs from A=3 and higher nuclei, and A=4 and higher, and then A=3. And this is from a talk by another postdoc at Berkeley Lab, Tyler Haig, and who's an experimentalist who was on the marathon experiment and others. And his whole talk was light nuclei are weird. So the ratio of neutron proton to proton pairs does not follow the pattern for these A=3 nuclei, and the EMC effect, although I don't think they published the EMC effect, precision EMC effect on A=3 yet, but that also seems to be weird. So this is it's just something that's sort of encouraging. It doesn't really necessarily mean it at this point. Anyway, and that's all. Thank you very much.
Do you have time for questions or?
Just a question here. When you talk about the Fermi, you have a slide talking about the Fermi energy and the momentum reduction, depletion.
Mhm.
If you go there, the argument is saying that the Fermi energy is not changing when you have a binding energy, but instead you're changing the mass.
Yeah,
So why
exactly.
why is
Yes.
that?
Well, I mean, the whole thing is sort of fuzzy, right? So what I'm saying for the Fermi energy is I'm saying that the energy difference in between the two populated states is 200 MeV. So you can have a scalar diquark with the valence quarks with the third valence quark, or you can have a spin 1 diquark 200 MeV more massive with the valence quark pointing opposite to it. So this is an assumption, and I was just playing with the numbers to see how the momentum would be affected if I could make these assumptions, but I actually don't think that I can.
If I take this Diquark production mechanism as the explanation for VMC, that means that PP and NN short-range cooperation are not going to create VMC effect, only NPs.
No, not at all. Why do you say that? One of my slides
Because
told
you
you.
cannot create a UD from a PP.
Which you can. Why not? It's quite easy, don't you think? There's a proton.
You can if you assume that the wave function is quarks, but not if it's two quarks.
Yeah, yeah. So if you assume that your protons are in a quark diquark configuration, then you are totally right. The only diquark that can form is this higher mass up isospin triplet, spin triplet. But that's not the one I'm using. So yeah, I mean, if you are in what was your point? What did you say again?
I say, my guess is that if the UD pairs
Yes.
are the main reason, that probably a proton is mainly a UD plus U, and a neutron is mainly a UD plus D.
So you're saying beta is much bigger than alpha?
This should be big in order for the two neutrons to be close together and pair to be produced to be a major case. Then I assume you also in the ground state of the proton, the neutron, those pairs should be important component.
Well, I guess for me that
This is the case that the NP
yeah.
can easily create another cell of the pair. But the PP or NN
Can I add something?
less.
Yes.
So when you write alpha and beta, are you assuming alpha and beta are constant, or are alpha and beta somehow radio dependent? Because who says that the radio part of the wave function and
Oh my goodness, Sebastian, come on, these are not radio dependent. I can't do that for sure. No, these are constant. This is an approximation saying that these are constant in time.
when you're talking about short range and them being close together, why is that? I mean, why can't they be radio dependent? And
This is in
especially-
Fox space, I think.
Yeah, this is in Fox space, right? But
So are you
But this is
talking?
only part of the-
Are you talking about the? We're looking at a proton here. Are you talking about the neutron-proton system or the nucleon-nucleon system?
you write P there, right? And you write P as this cat of 3 quarks
Yes.
with some amplitude.
Yes.
But the proton also has like a spatial part of the wave function. This is only sort of the isospin part of the wave function. But who says that you cannot have a mixture of this, the radial dependence of the wave function and the isospin part?
I don't understand. So how is it helping you conceptually to put beta of R in alpha of R?
Because when you're saying talking about short range correlation, then you're talking about putting them together. And this argument about, yeah, if you assume it's predominantly quark diquark,
Yeah.
then you have this problem with the proton-proton that you can only form the UD across. But isn't it possible that alpha and beta might in fact be radially dependent, and as they move together, it moves from a quark diquark to the quark, and then you have more being actually great.
No, I understand. Okay. No, now I understand you. So the ultimate goal for this thing is for the EIC the ultimate goal for the Diquark model is to say why 20% of nucleons are in short-range coordinated pairs. Why is it not 2%? Why is it not 50%? In order to answer that question, I don't think of it as these guys depending on or, but basically it's the exact same thing. You need to know the geometry and the structure, internal structure of a proton and neutron to know how close things come to each other.
I mean, it is an assumption that they're constant, but if you relate this to say this PDF calculation I showed, that the wave function of a nucleus is a superposition of all these sorts of channels, right?
Yes, yes.
And there is a radial dependence. The radial dependence is different for these channels.
I have not seen. Are you talking about this? Look at the top one. The top.
Yeah. So here, like, what if you? So this is a cat, right?
Yeah, you have. He's talking about projecting this to configurations.
Okay. Okay.
And then what happens to the coefficients? Why are the coefficients independent of R? Like, project this cat onto configurations.
Why are these?
No, there's no, but your alpha and beta. If I take, what if I want P of R, wave function, I project this P thing into.
Yeah, because I'm not doing like the geometry or I don't know the internal structure of physical structure of a proton and a neutron. I don't know that. I just know that these two group theory configurations happen.
Right.
But is that information that I want? Yes, it is.
That's sufficient. And there's no, when you're talking about short-range correlations, it's fine to assume that these configurations stay. They don't depend on how close these two nucleus are.
Yes, it is totally fine to do that, but in order to determine why only 20% of nucleons form these short-range correlated pairs, I'm going to need to know the radial, I'm going to need to know the internal structure of these guys.
I was maybe proposing it as a solution to what you brought up, to say like that doesn't seem to give that, but then you're saying if they move close together, and I was wondering, can the coefficients change? Okay, but maybe deduce that, but you were not having them close together, and then it would be consistent with the picture if you just assume that it could be quark diquark at that distance scale, but maybe as they get close together, it might change. And then I was providing it not as criticism, but as a potential solution.
That's interesting.
Yeah, you can also look at momentum space, right?
But Elena, why did you say we can already do that? Can you really?
Huh?
You said we can already do this, or did I?
Yeah,
misunderstand
I
you?
think I'm having a lot of flashbacks to what we are doing. It looks a lot like classical vibration.
So now, so this is in part. Okay, this is Simonetta here. Sorry, this was in part. I mean, this has been looked at the nucleon level. So at the proton and neutron level, how the various components, give you the different flavors of the structure function, right? So that enter the structure function. So U and D quark distributions, but it hasn't been looked at in the context of nuclear correlations, and that's what Jennifer, and I are working on. So, however, playing around with the composition of how much D quarks you can generate that way, that is something that has been that can be done with this type of wave function. So
Simonetta, that's very helpful. I understand what Sebastian was saying.
Yeah, sorry, I didn't explain.
No, don't worry.
But we're bringing it to the next level now.
Yes, right.
So, yeah.
Thank you. And Stan, do you have a question?
Yeah, just some comments. One of the important formalisms now is light front holography. It gives you the color confining potential, gives you the quark diquark structure of the proton and so on. But it also gives you a complete description in the front form. So it's relativistic and frame independent of the structure functions, the light front wave functions of the hadrons. It reproduces all sorts of phenomenology. It gives you the degeneracy between the Regge trajectories of the baryons, the mesons, and the tetraquarks, and exactly how they're related. And it's really a tremendous advance actually in physics, because it tells you the color confinement potential, tells you the form of the running coupling at all scales and so on. It's all based on one ansatz, which comes from light front holography. So many of the things that you talked about today, Jennifer, you could do in that formalism, and it'd be completely relativistic, frame independent. one major difference from what you're discussing is that the proton actually has, it's not just a quark diquark, it also has a quark, it has it at L equals 0. It also has an equal contribution at L equals 1. And this will change some of the things that you're talking about. In fact, and this gives you, this is how you get the spin-dependent structure functions of Sivers.
Okay. Stan, I'm just going to write out what you just said for the protons. Oh yeah, this thing. Because I like that. So for good, I'll write here. Thank you. Okay, so what Stan is saying is like for holographic light front QCD, you have beta equals 1, alpha equals 0, but you also have another split. Where can I do it?
Wherever you want. You can change the color.
So green is good. Okay, so this is that side of the proton wave function in holographic light front QCD. And this is going to be equal to, this is a quark diquark. I'm not going to put the flavors in. Where, well, sorry, 1 over square root of 2, we know the coefficients here, plus 1 over square root of 2 times the quark diquark with L equals 1 orbital angular momentum.
Yeah, with L equals 1,
So
right?
valence quark and the orbital are going opposite. And did I write it correctly?
Yes.
Yeah, and that has very interesting effects too, that wave function.
Yeah, I wanted to mention that, right? But it is interesting that we have a model for color confinement, which allows you to do calculations in all sorts of new ways. And it's all frame independent, gives you the right distribution amplitudes, light front wave functions, and so on. It's all based on one simple ansatz for the color confining potential. So just wanted to emphasize that point.
Thank you very much.
Actually, that comment from Stan is very helpful because I was going to comment on the momentum or the spatial dependence and how that might be necessary in order to get L equals 1, which is necessary to having orbital motion, which we know is there in the proton from its anomalous magnetic moment. Also, something that I didn't realize when I had a comment the last time you were presenting here. So the axial diquark was really important to getting the correct anomalous magnetic moment in the MJL model, but the MJL model also doesn't really have proper orbital motion because it's a contact model. Something like this model where you have proper orbital motion because you have L equals 1 states could probably actually produce the correct anomalous magnetic moment without needing axial dynamics. Of course, that would depend on a detailed model calculation. Maybe Stan's done that. But
or would be happy to do it, yeah.
Yeah, L equals 1 might actually be sufficient, and then you wouldn't have to worry as much about axial diquarks.
Yeah, and when you were talking about the spin 1 diquark contribution, were you talking about this wave function? Is this your definition of the spin? Okay.
Yeah.
Good. Okay, awesome. Any other questions? Okay. I'll see you guys in the
So let's
afternoon.
just break for lunch and in just under 2 hours, we'll have a discussion session. So all the people on Zoom are welcome to join us. We'll be at the same Zoom room.
Bye,
Do you want to
Stan. Bye,
continue?
Stan.
There.
Yeah.
No, she said she
Okay,
left
okay,
a couple minutes ago.
Thank you.